Our next speaker is Kaitlin Kratter. Kaitlin's a professor in the Department of Astronomy at the University of Arizona.
Is there a remote somewhere? Did that disappear? It's fine if it.
Right here. It'll only advance your slides.
Yeah.
I will tell you when there's 3 minutes.
Okay, great. All right. Well, first of all, I think Mike did leave out the precursor slide to his Charlie Brown and Lucy cartoon, where the observer went to the theorist and said, hey, we really want to go out and look for exoplanets. Can you write a couple sentences in our proposal about why we can do that and it's useful? And the theorist said, well, there's all these caveats, but maybe you could learn something about formation under a very limited set of circumstances. And then the observer revised the proposal and cut out that first part and just said, we'll learn about formation. So that's why Lucy took away the block. Okay, so see, it's a theory audience here. I know my crowd. So I was going to be a total delinquent and tell you about a project that didn't have a whole lot to do with atmospheres, but then I thought the better of it, and I'd save that for later. So my title in the program is incorrect, in case you looked at that. What I'm really going to talk about today is photoevaporative mass loss from hot Jupiters, and specifically I'm going to focus on a project led by a graduate student at the CFA, Anjali Tripathi, in collaboration with myself, Ruth Murray Clay, and Mark Krumholtz, looking at 3D simulations of mass loss. And so I'll just start out with a quick review of some of the things that Ruth talked about on Tuesday. If you recall, she talked about there's multiple ways you can get escape from both solar system and exoplanets. And the type of escape I want to focus on today is the kind that's relevant for hot Jupiters, where you have a hydrodynamic outflow that is driven by the EUV photons from the star. And so the idea is that you launch a hydrodynamic wind because you have EUV photons that are absorbed in the atmosphere, they ionize hydrogen, those electrons bounce around, they collide, they heat up the gas gets hot, and you get a pressure-driven outflow that can be modeled as a fluid wind. And so I'm going to show you some three-dimensional simulations of this process. And recall that this is motivated by some really neat observations starting about a decade ago, where we actually see signatures of mass loss. And I think Jacob may talk about this from the observational perspective a little bit more tomorrow morning. But the basic idea here is that if you observe a hot Jupiter transit at specific wavelengths, say something like Lyman alpha, you can get a 10 times larger transit depth, which suggests that you have a large neutral hydrogen envelope that's sort of beyond the optical radius of the hot Jupiter. In the case of HD 209458b, it's about a factor of 10 times larger, the transit depth at Lyman alpha as compared to optical. And so the interpretation is that you have hydrogen gas that's all the way out to the Roche radius of this exoplanet. Okay, so the other thing we know about hot Jupiters is that we think they should be tidally locked, where there's one side that's getting constantly blasted by irradiation from the star and a dark, colder night side. This is, of course, why Kristen spent the last few days talking about these very, very interesting circulation models. And so what this should immediately tell you is that the heating and therefore all of the features associated with these flows should be somewhat asymmetric, because you have one side getting blasted and the other side not getting any of these photons. And so if you want to be able to really interpret this transmission spectroscopy, you need to go to full 3D to really understand what these hydrodynamic flows are going to look like. And I'll just start out with a big caveat here, which is that the simulations I'm going to show you should really be considered as sort of a proof of concept that you can do three-dimensional hydrodynamic simulations of mass loss. And the thing we're emphasizing here is self-consistent heating by photoionization and launching of the wind. So there's a lot of physics that's not included in these simulations, things like magnetic fields, the stellar wind, charge exchange, and all of these processes are going to be really fundamental to understanding the details of these observations. But we're going to start out with a simple model so we can understand sort of the basic three-dimensional structure from self-consistent heating and a hydrodynamic outflow. Okay, and so one of the reasons why we have to start simple is because solving the full problem hydrodynamically is very challenging because of the scales that you need to resolve. So again, for most of this week, you've been hearing about atmospheric models where people are just modeling the little upper layer of an atmosphere. You know, we saw those beautiful pictures where we saw Earth and you saw how thin that layer is. But if we want to model both the launching of the wind and the wind itself, we need to resolve both the upper scale height of the planet and we need to resolve the large scale flow around the planet and in between the star and the planet. And so just to give you a sense of scales, if you want to resolve the upper atmospheric scale height, that means that your resolution element in your simulation needs to be 1,000th or 100th of a planetary radius. And if you want to see what the flow is doing on larger scales that's going to affect your observations in transmission spectroscopy, you need to follow that flow on scales up to, say, 10 planetary radii. And so now you're talking about, say, 3 or 4 orders of magnitude in dynamic range that you have to be able to resolve in your simulation if you really want to understand this problem. And so that's a challenge. So how do we go about doing that? So for the case I'm presenting here, what we've done is done 3D static mesh refinement, so that's what SMR stands for, hydrodynamic simulations with ray tracing to track the photons coming from the star. So I'll go through each of these pieces now in a little bit more detail. So we start out here on the right with our computational domain, and at the center of the domain we have our hot Jupiter. And the parameters for the simulations I'm going to show, you can think of these as being sort of like a WASP-17b for those of you who are telephone number memorizers in the room. So anyways, we have a sort of lowish mass hot Jupiter with a relatively puffy radius, and we're just going to resolve this very, very upper layer of the atmosphere so that we have a nice neutral reservoir of material to launch with the wind. And then we have a fixed inner boundary condition here so we don't have to resolve all the way to the interior of the planet. And this entire box is assumed to be co-rotating with the planet, and so the star is always going to be on the left side of the box. Now, as you can see, there's all these little squares here, and those are the actual bits of the mesh that we're using to solve the hydrodynamic equations. And what you can see is as you go from these red squares all the way down to the yellow, each of these individual squares gets smaller and smaller. And that's the static mesh refinement. So we have a factor of going from a factor of 2 smaller at every subsequent box here. So we resolve the largest scale flow with relatively coarse grid cells, and then we resolve the upper atmosphere of the planet with relatively fine grid scales. And so you've got by doing this, you are able to capture the flow on sort of a wide range of scales in your system. Okay, so that's your computational box that's, I lost, oh, it's back. Okay, so this is the box that's co-rotating with the planet, and then we introduce single frequency photons on one side of the domain coming from the star, and we only do transport in one dimension, so this sort of leaves out a little bit of the spreading that you might expect in reality, but it's a reasonably good approximation because the planets are relatively close to their host star. The star itself is only included by a stellar potential. So we have the star's gravity, the planet's gravity, so we have tidal gravity included. The Coriolis force is not included in these simulations, although it will be in subsequent work. And for the scales of these boxes, it's probably not that important. And so one thing we can do is start to make comparisons between the 3D simulations and 1D steady state models so we can see where we have deviations between the full results from asymmetric heating and the simple 1D case. So what I'm going to show you now is a movie of this simulation, and the big box here is just showing you density. The lower right box is showing you the neutral fraction, and the upper right box is showing you the line of sight velocity. So observers would be over on the far right of the screen, the star is on the left, and you're going to see the outflow being launched and slowly growing to fill the box. So the fluxes coming in this way. You can see that there's a higher density flow expanding starting on the day side of the planet. And if you look at the neutral fraction, you can see that you have a large, relatively highly ionized region in white, and then the planet creates this very, very strong neutral shadow where no photons are able to penetrate and ionize the gas. And so as we go across a couple sound crossing times here, the simulation is run for about 4 sound crossing times, and the sound crossing time for these parameters is basically the same as an orbital period. So you can think about this as the Jupiter going around the star about 2 times in this movie and about 4 times in the entire simulation. And it reaches steady state after about 1 or 2 orbital periods. So you can see at the end, when we reach steady state, the outflow is now expanded to fill the box, which is 5 planetary radii on each side. And we maintain this very, very asymmetric structure where we have ionized gas sort of on the day side and above and below the planet, and a neutral shadow beyond. Just to give you a sense of what the velocity structure looks like, these are just 2 snapshots from later in the simulation, going from left to right: density, neutral fraction, temperature, and again, line of sight velocity. You can see that strong neutral shadow, and you can also see very clearly that the velocity vectors on the density plot are, again, not at all symmetric. So we have very, very interesting structure in the flow. Just to zoom in on that a bit more, you can now start to see some of the really interesting hydrodynamic effects. So if you focus, sorry, the laser pointer died. If you focus sort of right at around the terminator of these 2 planets, you can see we're starting to develop these very interesting sort of turbulent rolls. And one of the really neat things that happens is that even though you don't have any photons getting to the shadowed side of the planet, you blast the day side of the planet, and the ionized gas travels around into these little curls and introduces ionized gas into that neutral shadow. And also, because there's a collision and a stagnation point, you can see the velocity vectors sort of disappear a little bit behind the planet. You have these 2 converging flows, and that turbulence and the converging flows here and here, that's the stagnation point, it actually substantially heats the gas in the shadow. So even though this gas is still primarily neutral, it's actually hotter than most of the rest of the gas in the box because of this heating here. And it's also very time variable. Now, this is one place where the omission of the Coriolis force may have an impact on the structure. Now, the scale of this box is small enough that we wouldn't expect a whole lot of curvature in this outflow due to the Coriolis force. That's going to happen sort of at maybe another 1 or 2 planetary radii out here, and that's just because of the velocity of the outflow, and sort of you can calculate what the length scale of curvature would be, and it's about 5 planetary radii for these parameters. But the Coriolis force may contribute, sort of take away from some of this symmetry, and may change the shock structure a little bit. But nevertheless, we're starting to see some very interesting, again, asymmetric features even in this simple case. The other thing that we can see in these models is that the outflow is indeed transonic, which is exactly what we would expect. So these blue lines here show the sonic surface. This is where the gas reaches the sound speed. The dashed lines show you where the velocity reaches the escape speed. And these purple lines show you the Roche radius. So this is exactly what you would expect for sort of a Parker-like wind, where you're pushing the gas out to the radius at which it becomes unbound from the planet. Now, despite all of these sort of interesting structures that arise from this strong day-night difference in the irradiation, the 1D models that go through the substellar point are actually really remarkably good. So these are 1D models from Ruth Murray Clay's 2009 paper. The black lines here show the ionization fraction, temperature, velocity, and density as a function of the line of sight direction, we label X here, from our simulation. So black is the simulation, and then these dashed lines just show the simple 1D model. So you can see that the matchup on the substellar array are just really, really good. And in fact, with a simple geometric correction, you can use these 1D models to capture the mass loss rates. And that's a really good thing, because it's a pain to do an expensive 3D SMR simulation for every different hot Jupiter that you might want to study, but you can at least get, in the non-magnetized case, a reasonable estimate of the mass loss rate. So the final thing I'll show you is that the other thing that's really cool about doing these 3D simulations is we can actually directly calculate Lyman alpha absorption, and with a little bit of more post-processing, one could do other lines as well. So what you're looking at here is the obscuration, and again, you're the observer looking sort of down the barrel towards the star. The star is the dashed line here, and the red shows you the fraction of the stellar disk that's going to be obscured by this outflow, and you're looking at it as a function of velocity away from line center, so minus 45 to 45 over here. And you can see near line center, the obscuration is enormous, but by the time you get out to around 50 kilometers per second, you basically have no obscuration. And so the important point here is that we are not reproducing this kind of mysterious large velocity absorption seen in this original observation of HD 209458b. Now granted, the parameters of the planet are a little bit different, but here you can see it more simply where this is now wavelength or velocity on the x-axis and the sort of integrated obscuration fraction. So again, if you were replicating the observations, you would see peaks out here and here, and we don't see that at all. That's not unexpected that we don't see it, but it's important to point out that there are other physics that must be going into producing those large velocity offsets. So with that, I will just put up my conclusions and say that self-consistent wind launching simulations show interesting asymmetric structure, particularly this driving of the day side flow wrapping around the night side of the planet. And eventually when more physics is put in, this is something that John McCann, who's soon to be a graduate student here, is working on, including Coriolis forces, MHD, and stellar winds. I think we're going to see some really interesting observational modeling tools at our disposal. And I should also point out that James Owen and Fred Adams have also done some really interesting work on this, especially focusing on the role of magnetic confinement, so you should talk to both of them about that aspect of the problem. So I will stop there and take any questions. Mike. So what we're doing is basically shooting a bunch of single frequency photons in one end of the box and then computing sort of the optical depth and calculating heating and cooling based on the on-the-spot approximation and a cooling function that's appropriate for whatever the composition of the gas is. So it's relatively simple. For calculating the actual line profiles, we're taking the temperature and the ionization fraction and just calculating a Voigt line profile and integrating it up over the line of sight. So it's not a Monte Carlo radiative transfer scheme at all.
Well, I mean, you're not doing a Monte Carlo radiative.
I'm not as familiar with their models, but maybe James is. I think he's going to. It has different. This is hydrodynamics with optical depth calculations. It's not doing. Yeah, I'm not familiar enough with their calculations. Right. So and the hope is that when the Coriolis is put into this, you will get the self-consistent launching of that tail hydrodynamically, but there's not enough chemistry in that to do that kind of calculation. It's because there was no obvious reason why a hydrodynamic wind should reach velocities of 100 kilometers per second given the escape velocity from a hot Jupiter. Right? So the fact that we don't see a bunch of material there is not inconsistent with a simple hydrodynamic outflow. So this is why people invoke things like charge exchange and the stellar wind, right? So the stellar wind could be coming in at a much higher velocity. So if you have some other component in your flow that has high velocities, you could imagine creating absorption at those high velocities. But the outflow launch from the planet is at tens of kilometers per second.
So you can include a magnetic field of what primary effect
I think the short answer is a lot, depending on the field strength. So, and depending on the field configuration. So this is something that James and Fred have looked at a lot in 2 dimensions. But you can get magnetic confinement of the flow. You can actually suppress wind launching from certain, from the polar regions. So it can dramatically change the mass loss rates. And it can change whether or not your flow is sort of in this energy limited regime or in, as I think James calls it, the photon limited regime. So there's a whole host of issues that come into play. And those are probably really important for understanding the variety of the observations that we're likely to get in the coming years. This is Athena, which is a Goodenough hydro scheme. So it's the linearized row solver. Is that what you were asking? It's a Riemann solver. So, yeah, we can talk more about the details of the hydro scheme, I think, offline if you like.